Um, Fantastic. So it's our fourth session today, and uh, this time we're going to talk about something very interesting. Well, it doesn't mean that previous sessions were not that interesting. However, this time we're going to talk about how to deploy your own token. And I think that this session should be particularly carefully listened to, at least as if you wish to one day to have your own token. And Ma today will tell us how to do that. Ma, floor is yours.
Oh, yeah, thanks. You're traveling?
Yes, a little of a travel from
Cool.
one, part of a city to another one.
Yeah,
Okay,
seems the weather is quite good.
yeah, pretty good.
Cool. So let me lead the content left behind. So today we're gonna continue to the last course's content. So in the last course, we talk about how to um, deploy a very simple smart contract to store something. We create something like smart contract and create a variable to contain the value we want to store. And then we have two functions, okay? One for store the value, another for the retrieve the value. And today we're gonna talk about how to issue a token. And this token is mainly based on the ERC20 standard. And then I can discuss with you a more complicated case that how to integrate the token with some other additional functions. Like if you want to use the token to be as the reward to upload some data and in the case that if somebody is submitting some data to your smart contract and then you give him some token as a reward. And in some other cases, like if some users want to um, retrieve the data, want to use the data, then he need to consume, he need to pay some token um, as a way of consumption of the token. So this is what we're gonna do for today's course. And let me share my screen. So firstly, okay, so firstly, in the last course, we still have some remaining things to discuss about layer two. Let me quickly go through this part of the content, and then we shift to the token deployment. Okay, so in the last course, we talked about the Ethereum, and Ethereum is the layer one. Okay, why is layer one? So at the time of 2020, a lot of people is entering into the Ethereum network and trying to deploy smart contract on it. At that time, one ETH worth several $100. So as you can see that if you are doing something on the ETH at that time, even though the ETH itself is cheaper than now, um, if you are doing a lot of the transaction, then it will be very costly. And as you may remember, the block time of Ethereum network is 12 seconds per block. So the ability of the network to process the transactions per second is also very limited. Therefore, the Ethereum conditions are considering how to enhance the scalability and the speed of the chain. And there are several solutions. And one solution win a lot of the attention in the end, which is the layer two solution. So what the meaning of the layer two solution? You can think about the Ethereum network, the main network is the highway, and submitting transaction on the main network is just like you drive your private car to the highway and drive along the highway from one point to another point. Okay, and if there are many people entering into the highway, then the highway would be very crowded. So the layer two is like now there are some public transportation. So there's a new company which is operating the bus business. So a lot of people can ride a bus, and the bus can ride a lot of people onto the highway. So in this case, the highway can transport more people, and at the same time, the transportation fee would be lower. So this is the main logic of the layer two. Okay, so in technical words, the layer two is just like to combine a bunch of transactions on the layer two network and then put them on the layer one network, which is Ethereum. Okay, so in this way, you can say that the layer two is also a blockchain, but this blockchain is very centralized because you can think about the case is that layer two is just like what is inside the bus. So inside the bus, the bus driver can command everything, right? So it's quite centralized. So it's just like the bus driver will organize who will see which on which set and the priority of the transaction. So that's what we say that the layer two is a solution to solve the problem of the scalability and the transaction speed. Okay, so the transaction speed here you can understand it as a congestion level of congestion of the highway. So if there are all the bus driving on the highway, then it's less crowded. So uh, people can drive in a high speed. Okay. Yeah, this is the mainly what we talk about for the layer two. And there are mainly two solutions under the layer two. Okay, one is the ZK optimistic rollup, and one is the ZK zero knowledge rollup, and another is the optimistic rollup. Okay, there are two. And under here, the two solutions, there are a lot of independent network, and you can check it by this website, l2bit.com. Okay, lb2 dot l l2bit.com. Okay, search for this website. Um, Let me check. It will gives you some data, like it will list all of the layer two solutions. And here the stage means some milestones that this underlying layer two solution has achieved. Okay, so these stages are made by Vitalik. So if some of the stages, so the more stages the layer two solutions achieve, then the more mature this layer two solution will be. Okay, which means that this layer two solution will be more secured, more reliable, more stable. Okay, and you can check for it. So you can, and as you can see that there are a lot of layer two solutions now. Okay. Actually, more than this, because this website only include the main layer two solutions, I think. And the first one is Arbitrum, and the second one is a Base. The Base layer two is constructed by the Coinbase exchange in the United States. Okay, and the Unichain is the layer two chain launched by Uniswap protocol. Okay, some of you may heard of Uniswap protocol. Is the first decentralized exchange protocol launched on the Ethereum network. So it will support the trading of the token on the blockchain. Okay. And then let's see something about okay, I will jump some pages because for some pages it's too technical. And for this stage, I think you can skip it.
And will we discuss in details this fantastic base solution perhaps later, or maybe you will say a couple of words now? What are the
uh,
advantages of such a solution?
Yes, I can talk about this now. So here the optimistic roll-ups. So there are, as I said, there are two techniques or technologies behind mainly types of technologies behind their two solution. One is the optimistic roll-up, and another is the zero knowledge or ZK roll-up. And the benefit and the base blockchain is actually supported by the technology of optimistic rollup. So what is the advantage of optimistic rollup? We need to firstly talk about how it's working, right? So think about the case that I'm operating a optimistic rollup blockchain. So I'm a centralized server, which means that there are only one server in this blockchain rather than many nodes supporting a blockchain. And we call it the sequencer. Okay. So the users will submit their transaction to me, and I'm a sequencer. I will combine and ordering these bunch of transactions according to the gas price or gas fee they give in their transaction. And then after combining this bunch of transaction, I will submit this transaction to the Ethereum main network, and I will assume there is no fraudulent activities inside each of the blocks I constructed. Okay, and I'm waiting for 1 week here, 1 week for any challenging, okay, for the submitted blocks. So in this case, is the main logic is that I will assume all the transactions follows the correct things. Nobody is do some fraudulent things unless there are somebody challenging that some transactions is doing the wrong things, and then people are gonna check, and if his are correct, we're gonna revert the transactions, okay, back in time. So this is how the optimistic rollup is working. So the benefit of this way is that it's very quick because I don't need to check the correctness of the transactions. I only wait for some third parties to challenge. So this is very quick and easy to achieve. Okay, and yeah, so this is a benefit. And as you can see that the performance for the performance, the OP, we always call the optimistic rollup as the OP rollup. So OP can offer massive scalability gains, okay, and don't have very heavy computation because I just assume all these transactions are correct. Okay, I don't compute anything, okay, for a sequencer. So that's why it's very easy to deploy layer 2 blockchain in the OP rollup. And then technology or the developing requirements is relatively low. Okay, so any questions?
Yeah, is it correct way to understand where this scalability comes from? Is that major problem, at least before Solana was widely introduced, is how to make a sequence of transactions inside one block. And Solana made a revolution of proof of history when they kind of tried to address this problem of putting transactions, like introducing time dimension inside the block. And in essence, Base also tries to solve this problem somehow. But this problem is solved in some sense centralization, because you have a central agent. You called him
Right.
sequencer, right?
Yes.
So it's kind of a combination of the centralized system and centralized, because now you have a central agent who actually is responsible for ordering transactions inside the block. Is it correct?
In some sense, it's correct. But there is a trade-off between the decentralization and the security, or the not the security, between the decentralization and the speed and the scalability. You talk about you mentioned the Solana network, right? And the Solana network is more scalable and with high speed transaction processing ability. But the trade-off is that it only has thousands of validators or nodes. So in this case, the trade-off can be understood as the more validators there are, the more decentralized your network is. But the more, at the same time, the more validators there are, the communication needs will be there among the validators because you need to do the consensus. So every validators need to know what the other validators is doing. And this heavy communication needs will uh, make the whole network very slow. So there is always a trade-off, okay, between the decentralization and the speed. Okay, even for Solana there is, and for layer two, it's a very extreme example because it's a totally centralized network, only have a sequencer, and so it's very fast, very quick. Okay. Yeah, but yeah, but I think you are right. Yeah, you are right.
And
And
the question is about also the programming language. So Solana, as I remember, correct me if I'm wrong, but Solana used Solidity. Is it correct?
yeah,
And
no, so Solana used the Rust.
is
So, yeah,
their own kind of. Okay. So they use Rust and Base uses what?
Solidity, although you can call it EVM compatible. So it's the same like a virtual machine on Ethereum.
Hmm. And what about coding everything that is needed to build to deploy your token? So what language you need to know in order to create your own token? If
Okay,
you
so
if you're thinking of the different possibilities, so you can try to base it on Solana somehow, or you're thinking of Base. What will you need to know?
So every time you see a blockchain is labeled as EVM compatible, it means that everything you can do on this chain will be same with what you can do on Ethereum network. So on Ethereum network, as we talked about in the last lesson, we write Solidity contract. And the Solidity language is a high-level language. There are actually some other languages in the same high level. And you are using a compiler to convert the high-level language to some um, machine readable language. Okay, machine readable code. Okay, by the byte code. Okay, this is the way how the EVM is doing. So EVM is actually a interpreter uh, to like decode your high-level language step by step to the bytecode. Okay, and for Solana, because it's a high-speed chain, so the underlying consensus mechanism may be a little bit different. And I think they chose Rust as the native programming language on that chain because the Rust is the low-level language. So in that way, they can save they can save some uh, like room or computing power as you may say that if you are using Python to do programming, it's actually quite slow. But if you shift to C++, then because before we run it, the code are pre-compiled, right? So it will be much faster. So that's why the Solana is much faster. And I see some questions in the chat box. Okay, so let me firstly answer the questions. So the first question is, are all the transactions are conducted under optimistic rollups, or for some example, some percentage of the transactions? Okay, so good question. So the layer two blockchain also is a layer two of the Ethereum. It's an independent blockchain. Okay, so the independent blockchain means that it has its independent storage, computation resources, and everything. So it works independently. The only thing related to the layer one is that the transaction will be combined and uploaded to layer one as a proof. Okay, so only something like a receipt of the transaction would be uploaded to the layer one. Okay, rather than the whole story of the layer two status would be uploaded to layer one. So think about the case that all the things will be uploaded to layer one. Then the whole system will also be very slow because the uploading load will be very huge. Okay. And then the second question is that all it somehow depends on the specific chain. I think in all the cases that the relationship between the layer one is and layer two is that the layer two will submit some receipt of the transactions as a proof to the layer one. They will not submit everything. Yeah, thank you. Yes, so let's go on. And then we just now we talk about OP rollups, right? And then we move to the zero knowledge rollup. So the OP rollup is waiting for some other people to challenging the validity of the transaction, right? But the zero knowledge rollup is validating all of the transactions at the stage of submitting the transaction proof to the layer one network, the Ethereum. Okay, so then it means that there will be a lot of computation works, a lot of computation burdens at the time when the network is submitting the bunch of transactions to the layer one network. Okay, so usually the network, the ZK network will be written into the chips directly to facilitate the speed of the computation. Okay, then that's why if you can see some firms which is doing the ZK network, they will recruit a lot of people doing the chip design, and so in this way uh, they can speed up, okay, and uh, and you can also understand in this way how computation intensive it is. Okay, and I think because the complexity of these ZK rollups, the usage of ZK rollups is not that widely as the OP rollups. So think about the case that you need to deploy layer 2 in ZK rollups. You need to hire a lot of people doing the engineering things to write the programs to the chips. And this is very hard work, actually. And also, there will be very easy to have some bugs. Uh, and if there is some bugs, your network will be not as that secure. Okay, and if we shift to the website we checked just now, here is the proof system. You can see that the first 01 like Arbitrum base are all OP OP OP. Okay, and some of them are ZK, okay. This one, they call the ZK as a validity, okay. The ZK sync area is the OP, is the ZK chain, okay. And the linear is also the ZK chain. And the unit chain is the OP chain. But the thing about the trading volume, let me check for another website, which is the DEX Screener, which will shows you as the dashboard about the trading volume of the tokens on each of the chain. You can see that there will be a list, okay? So the chain with the highest trading volume is Solana, and the Solana is layer one, and the second one is the Ethereum, and the third one is the base chain, okay? The trading volume of base chain is even, okay, it's even, okay, it's not the sequence, okay. So the trading volume of a base layer 2 chain is almost 2 billion a day. And here another chain with high trading volume is the Arbitrum. Okay, so Arbitrum has 600 million dollars trading volume a day. And then if we check one of the ZK chain like Linear, okay, the trading volume on Linear is less than 100 million. So it's not comparable with the OP chain actually. So that's why I think the complexity of the ZK chain is what prevent them to have a very high trading volume. And then, yes, so any questions? Because I don't want to dig too much into the techniques behind the layer 2 chain, as the ZK chain is very complicated. Although it's seem its trading volume or something seems okay. Okay, if there's no questions, I think we're gonna shift to the main content of this of today's topic, which is the programming things. Okay, how to issue your own token. Okay, another thing I remember. Okay, um, for every chain, if you want to communicate with the chain or deploy something on the chain, you need to have an entrant, right? The entrant we have is a node. So like in the previous case, we want to use the Ethereum node and Ethereum node. For the Ethereum node, we can use Alchemy or the Quick node. They gonna provide the service of the full node. We can submit the transaction to the node operating by the Alchemy or Quick node. And also, if you want to interact with the layer 2 chain, you can also register on this website and find a node. In most of the case, if your trading volume is not that high and the frequency of calling the node is also not that high, it's free of charge. Okay, so you can try this. The quick node is good, I think. My choice is quick node. Yes, and then we shift to our token. Okay, so last time we talked about how to create the smart contract using the user interface in the browser, and as well as how to write the smart contract and interact with it using Python language. But today I will mainly adopt to the Python language because the task here is more complicated, and I want to write the code tidy, and as well as the helper like classes and functions. So here I already write the token smart contract. Okay. So this smart contract, as you can see, that begins with a contract anonymous. Because our brand is anonymous, so I call this I create the token which named as anonymous. And this anonymous smart contract is something. So this is something is just like the heritage feature we have in the Python programming language. So if we said that this class is some of the other classes in Python language, it will means that this class will heritage all the functions from the parents functions, right? We see sometimes we see the heritage functions from the father class. Okay, and here the same. Okay, so here I import ERC20 Solidity contract, and then say that I will create another contract which is based on this imported smart contract. And if we check this ERC20 smart contract, you can search it in the internet. It's a predefined smart contract for the ERC20 token smart contract. Okay, so let's see what is inside. Okay, it will give you some details, but one thing you need to remember is that we call this a standard. We call it a token standard because there are some basic functions predefined for you to use, like if you create a smart contract based on this standard, your smart contract can issue some token to others and burn some tokens from some other from some addresses wallet. Okay, the burn means that to decrease the supply of the tokens. Okay, and then it also provides the function of transfer. You can transfer some of your holding tokens to some other addresses, and you can also check the balance of your tokens. As I said, okay, I think I have a slide for this. Okay, so wait a minute. Okay, so here it is. Okay, so this is the primer of the ERC20. So here in the last course, we talked about how how a blockchain is operating, right? And a ERC20 standard is actually a balance sheet stored in a smart contract. And every time there is a new transactions interacting with the smart contract, it will change the balance. Okay, so the balance contains the information of which address hold how many of the token. Okay, it's like this kind of thing. So if the user Alan has the initial balance of 10 token and he got another new 10 token uh, issued, then on his balance, the token balance will be increased to 20. Okay. And then if Alan transfer 5 tokens to Bob, then the Alan's balance of the token will be decreased to 5, and but Bob's balance of the token will be increased to 15. And then if we burn the balance or burn the token, like we burn the Alan's token balance from 20 to 10, which means that his token balance will be decreased by 10. So that is how we operating the token on the smart contract. And so this is the basic functions on the smart contract. Okay, so we can mint, which means that we can create a token from the air. Okay, we can issue the token to some certain people's address, and then we can let the people to transfer their token from one address to another. Also, we can burn a token for a certain address, okay, to cancel their use. And also we can let the users to check the balance of their token. And because the first three functions are changing the storage status of the blockchain, right? Because we are writing the balance sheet. So this kind of operation will consume gas because they are consuming the computation power. But the fourth function will not because it's only view the values or data stored on the blockchain. So the balance of like if you are checking the balance of your address, then it will not ask you. It will not consume a gas. You don't need to pay anything to this checking. Okay, so this is the basic things of the ERC20 standard. And if you want to write some smart contract based on the ERC20 standard, you need to firstly import, okay? And here we use this directory to import, and I will explain to you how to deal with this later on when we are going to compile this smart contract. Okay, and inside this smart contract, I add some additional functions. Okay, so the constructor is just like the init function in the class things in the Python programming language. Okay, so when you are deploying the smart contract, it's actually the behavior to create the instance of this smart contract on the distributed computing system, right? So at the time of the deploying, you are actually init this smart contract, and at the time of init, you can define some input in the init function. So here I have three parameters as an input when we are creating an instance of this Anominon smart contract. The first one is name, the name of the contract or name of the token. Second one is the symbol of the token. Okay, and the third one is the initial supply. Okay, this is the initial supply rather than total supply. Okay, and then is the admin, which means that who is operating this smart contract. Okay, so there can be no admin. Okay, the admin can do the things like to you can regard the admin as a guard of the this smart contract. Okay, if there's no admin, which then this smart contract will be operating by itself. But let's see how the admin is achieving things. Okay, and here there is a ownable modifier. Okay, and the ownable modifier is also imported from the repo of the OpenZipLink. Okay, so this OpenZipLink. You can regard it as the simple repository. It contains a lot of the standards of the smart contract on a blockchain. The ownable means that only the owner of the smart contract can call certain functions if you add this modifier to the functions. Okay, here when we are creating the smart contract, the message sender address will be the owner, which means that who deploy the smart contract, who gonna own the smart contract, who can call the only admin functions inside the smart contract. Okay. So I said a question. So if there is no admin who admin. Okay, so if there is no admin, that means that anybody can mint, or not anybody can mint. You still need to define who can mint. Okay, because here, as you can see that uh, I define the mint function to be operated by the only admin. Okay, only the admin can operating the mint function, can issue some token to some other bodies, and these uh, mint. Okay, the private mint function inside is the function inherited from the ERC20 standard we import at the beginning. Okay, and you can see that similar with the case with some other programming language, when you are adding this little signal at the beginning of the function, it means that this function is the private function. Okay, it cannot be called outside the class. Only inside the class it can be called, and um, we wrapped this private function inside the mint function, and the mint function can only be called by the admin. Okay, and for this question, okay, the question, if there's no admin who will mint, then it depends on how you define the mint function. Okay, if you define the mint function like I delete the only the main here, then everybody can call the function and the mint. Okay, mint token for himself. Okay, but if you does not define this function, then nobody can mint, and then zero token will be circulated in the blockchain. Okay, and also the burn. Okay, the burn is also wrapped another private function burn inside the function, and only the admin can burn some certain addresses token with certain amount. Okay, you can say that for both the mint and the burn, there will be two parameters. The first is the address, and the second is amount, which means that you can mint a certain amount of the token for some certain address, or you can burn some certain amount of the token from some certain address, okay? And then the final function is the update admin, which means that I want to hand over the power of the admin to some other address, okay? And this function is also only owner function, which means that only the owner can call this function. And this kind of smart contract can be easily written by ChatGPT because Solidity language has been there for already 10 years. A lot of people are writing this programming language. So you can just tell the ChatGPT like, I want to create a smart contract which use the token in some certain circumstances, and then the GPT will help you combine the ERC20 standard with some certain function to achieve what you want to do. Okay, and then this is the smart contract itself. And as we talked about in the last lesson, the the Solidity smart contract is just a human readable programming language. And if you want to deploy your smart contract on the blockchain, you need to compile it to convert the human readable high level programming language to the low level bytecode, which can be read by the machine. Okay. So these to achieve this function, I usually use the module I write. Okay. So I write a module called the contract deployer. So every time if I want to deploy some smart contract on the chain, I will directly use this module rather than step by step write the code in Python. Okay. As we said that if you want to compile a smart contract, you will use the function of compile standard in the Solix library in Python. Here the same, okay? Here it is the same, and let me check. Okay, so let's see the structure. Okay. So I have mainly three functions inside this deployer class. Okay, the first one is the compile, which means that I convert the Solidity language to the bytecode, which can be read by the machine, and then another function which can help me to create the transaction to deploy this smart contract on the chain. Okay, this is the second function. And the third function is the to create the instance which can be used by the Python programming language, okay, with a certain address. And on that address, the smart contract is deployed, okay. So this third function is actually can give you a case to interact with the existing smart contract rather than deploy a new smart contract. Okay, so let's say the first contract or the first function. Okay, so the first I will give you all the code. I think after class, so you can see how it's working. So the input of the compile is the source Solidity file. Okay, so Solidity file. And the content is the name of the smart contract. Okay, so for the last case, our token, then the name of the file is a token v1 dot solidity. Okay, and the name of the smart contract is a nominum. Okay, so this is the parameter of the first two um, things. Okay, and then the standard. Okay, So this function is actually used to produce the output of the compiling. Okay, and what I said at the header of the Solidity smart contract, we're importing some existing library uh, of the Solidity code, right? And this open sibling is where you can find it um, on the website. But when you are compiling it, you need to have the library existing on your local machine. Just like the case if you are writing some Python programming language, the Python script, and you import some library into your script, when you are compiling your Python script, your computer actually store all the library inside the environment, right? And we are compiling it. Your interpreter is actually include all of the library needed in the script and then compile it. So what you import at the beginning of your script is actually converted into real code at the end of the machine code that can be read by your computer. And the same thing here. We also need to download all of the Solidity smart contract we imported here, and we usually store it in a directory under our project. Here I store them in the lib. Okay, here you can see the open sampling. Here under the open sampling contracts, I have the lib. No, not here. Okay, let me check. Actually, right here, lib, and under the lib, there are things like a universal router or the ERC20 vulnerable lib. Okay, not here. Lib, let me check. The lib. Okay, okay. Um, Here in the smart contract, we are importing the library under the open sampling, right? So I just contains all the open sibling smart contract existing on the network in the internet as stored in the directory lib. And on the open sibling website, you can find their GitHub. So you can just pull all the open sibling contracts here inside your projects. Okay, so I do the same. I just pull their GitHub repo in my lib directory. And because here in our smart contract, we are importing the standard with the content like beginning with at open sibling. And if you directly compile this smart contract, the system cannot recognize this at open sibling. So you need to replace this open sibling to your local directory. Okay, because in your local directory actual there is an actual code can be replaced into your smart contract. Okay, so that's why I define these remappings in the compile input. Okay, so in the compile input, I define the add open sibling contracts here inside the smart contract. Okay, so this thing before will be equals to lib open sibling contracts under the directory inside my inside my current projects. Okay, so in this way, I can use my local code, local library to replace the things I define inside the smart contract. Okay, so in this way, the smart contract can be successfully compiled. Okay, so after the compiling, I can get a JSON file which represent the result of the compiling. As you can see that here contains some weird things, and it actually contains two main things. One is the bytecode, which can be recognized by the computing system, and another is the ABI. Let me check the ABI. Okay, the ABI is the format that teach you how to interact with the smart contract. Okay, because all the bytecode is not human readable. If you check the bytecode on the blockchain, it's just like a random sequence of the words. So if you want to interact with the smart contract, you need to have a map, or you need to have some instruction to tell you how to interact. And the API is this instruction. It contains all of the functions which can be called on the smart contract, as well as what kind of input you need to define. We are calling this function. Yeah, this is the API, and this JSON file is the output. Okay, so that's why I will write all of the output compiling things into a JSON file. Okay, in the same directory here. And then deploy, okay? So deploy is the same, okay, with the things I talked about in the last course. It's just like you send all your compiled bytecode to the blockchain with the transaction containing all the data. Okay, so this is the way. And one thing you need to care about is the gas. Okay, so in today's afternoon, when I'm testing the code, I find I cannot successfully deploy my smart contract even on the testing network or the local fork of the network. And finally, I find that it's because the gas I define is too low. Uh, because in the fork network, the transaction will not contain much of the information. So at that level, I don't know why, but at the end, try many times, I know that it's because my gas is too low. So the gas is the gasoline, right? The gasoline you put into a car, and the transaction is like journey. Okay, so that means the gasoline is not enough to support my journey. Okay, let's see the question. Why it is required to load the Git repo to live directory, and we can not otherwise install it like any other Python library. Um, on the Python, you can uh, install a library using the pipe, right? Because pipe is a tool to manage all of your library. And here, there's no such existing tool to do it because uh, I made the deployer by myself. So that's why there's no existing tool to do it. So you need to do it manually. So I also need to do it manually. And there are some existing tools to help you to do that. But I think in that the way of doing that is not that friendly to teach. Okay, so it's in that way it becomes the command line operation. Say if I want to write a smart contract, I write here, and if I want to deploy it, I input some command in the command line, then it is deployed. It's so abstract, and what you did is not recorded. I mean, it's not in the script, and it can be repeated, can be called once again next time if you are going to do the same. Okay. Yeah, so that's the main reason. And so in that way, you can see that um, the lib is actually a bunch of API that is telling your computer how to do with your imported standard. Okay. So uh, in one word, what is stored in this library directory is a bunch of file containing all the APIs of the existing smart contract that you are imported to your smart contract and heritage from. Okay, so this is how they are working. And yeah, so this is how to deploy. And the third function is like I know there is an existing smart contract on the blockchain, and I know the address of the blockchain. Okay, remember that in the last course, right? After we deploy a certain smart contract on the blockchain, it will be deployed at a certain address. Okay, um, and also we have the ABI. So in this case, we can create a local instance of the smart contract with the instruction of how to interact with. Okay, which means that there are some function inside the instance of the smart contract. It's a copy of the smart contract on the blockchain. The local version is that we can use it to connect it with the remote version. Okay, because the local version is supported by a certain library of the Python, which is the Web3 Py. Okay, if we have a local version of the smart contract, we can create certain command and transaction locally with our instance, okay, in the Python environment. And then after creating the transaction, we submit the transaction, and then we use the transaction to change the status on the blockchain of the certain smart contract. Okay, this is the why there is a kind of instance, the local instance of the smart contract in the environment of Python. Okay, so the usage. Okay, and so this is the third tool I made. I call it the contract deployer. And the third one I made, okay, and the third one I made is the API to interact with the token. Okay, so today I illustrate some tools I made, but the code inside is all the same with the case I described in the last lesson. So in the last lesson, I do it step by step in one script, but today I integrate some of them into the classes, into module, and then call this module outside in another script. I'm gonna show you how I'm gonna call this script, call this module in another script. But in the end, they are all the same. Okay. Although it seems a bit different, but in the end, they are all the same. So token API is specially designed for the smart contract. In the smart contract, there are four functions mainly, right? So to interact with the smart contract, the local API should also have at least four functions corresponding to the four functions stored on the smart contract. Okay, so let's see that we have actually more than four functions. Okay, so the first function is the import token contract. Okay, which means that we initiate the token API, okay, to tell the token API which smart contract we want to interact with. That's why we need to tell it the address of the smart contract, okay? And after it, we have the mint, we have the burn, we have the transfer, and the balance of, okay, as well as the update admin. Okay, so in the smart contract we define here, we don't I didn't um, define any transfer function because the transfer function is provided inside the ERC20 standard already. And because the contract of the Gemini is heritage from the ERC20 standard, so it will heritage all the functions like transfer from the ERC20 standard itself. So that's why I didn't define the transfer function inside the arbitrary function I made here. And then I also have an update and mean. So as you can see that inside the end of the function, like the mint, I'm actually just constructing a transaction and send the transaction to the chain. Okay. So I'm actually do the same thing as what I did in the last course. Okay. And I also define some functions as a helper functions to submit the transactions. Okay, this is the three main part to help you create the smart contract and also create the local helper functions and classes to help you interact with the function you deployed on the on the blockchain. Okay, and then here we have a test. We have a test the script. Okay. Here. Okay, so we can test it in the local forked chain using a glitch. Okay, so this is the same. Okay, this is the same. So firstly, we need the glitch fork. And then as you can see that I import the Nominate token and the contract deployer from the modules I write. Okay, because in the module direction, I already export the contract deployer as the module, and also I export the token API as a module with the name of the Nominate token. That's why I can call my module outside outside the module directory in another script. Okay, so I import the helpers. And after I have a need the glitch fork, I define something inside the script as a startup. Okay, so here I create the Web3 instance using the glitch URL. So which means I operating on the local fork of the blockchain. And then to operating or interact with the local fork, I need to have address, and I will init the address using this private key provided by the testing network. Okay, here the first one, and then based on the private key, I gonna have the public key, which can be regarded as the account address. As you may remember from the last course about the Bitcoin blockchain, the account address can be regarded as a public key generated by a private key. Okay, that's why only using the private key I can construct the account. Okay, and also I can check the balance of ETH. Okay, on this account. Okay, and then I will call the contract deployer. Okay, to call the contract deployer, I need to input some parameters. Okay, the first is the file's name. As I said, the file's name is the token V1, and the contract name. Okay, the contract name is defined inside the contract. Contract name is a nominum. Okay, and then use the Web3 instance I defined at the beginning, as well as the private key and the contract file directory, and the contract name. I can get the instance of the deployer. Okay, and then I compile. Okay, I call the compile function of the deploy firstly, and then I deploy it. Okay, because as I said, in the smart contract, once you deploy it, you actually need an instance of the smart contract on the blockchain. And once you are in need the instance, you need to give the parameters to the init function, which is the constructor function we see here at the beginning of the smart contract. Okay, the name, the symbol, the initial supply, and as well as the admin. And so here we name it as the anomaly and the label as ALM and the supply of 1 million. Okay, and the main address as the, let me check the admin address. Okay, and the main address as the sender address, which is the address generated by this private key. Okay, and then I deployed my smart contract. Okay, and then okay, so let's firstly deploy the smart contract. So after I run this script, you can see that it shows that this smart contract has been successfully deployed at this address. Okay, and if you shift to the terminal, the local fork of the blockchain, you can see that one transaction has been created. And in the information section, you can see that it says that one contract has been created, and the address is started by 6ECC something. And this 6ECC something is actually the address given by your smart contract deployed. Okay. And then we can see how we shift to the section of how to interact with your smart contract. Just now, I deploy it, right? Deploy it, use the contract deployer module I write in front in advance. And then if you want to interact with your smart contract, it will you need to use the anomaly token API I write inside the module. Okay, then let's firstly get the instance of this this API module. Okay. We still need to input some parameters for this instance. Firstly is the web3ness, and then the private key. The private key is the same, okay? And then the contract API and also the contract bytecode, okay? And then we have a token instance, okay? I name it as a token instance in the environment of Python. And then I import the address, okay, because we deployed the smart contract at this address, the 6ECC, okay, and I will inject this address to our token instance. And the first function we're gonna call is the mint. Mint is the mint function. So let me call it. Okay, then we see that the transaction succeed, and this will show the hash of the transaction. And the meaning of the transaction is that I will give this user account, here, this address, this much of the token. Okay, and if you check the terminal, we can see that another transaction has already been created successfully, and the transaction hash is beginning by EA85. And if we check the Python console, we can see that it will be the same with the hash shown here. And after the mint, we can check the balance of the account we give the token to. Okay, let's check. Okay, we can see that the balance of the account now have the same amount of token we give it just now, this amount. And then after giving it the token, we burn it, okay? Because now we are the admin, so we can do anything. We can burn it. We can give the token to its address, we can burn the token on this address. So we burn it. So let's burn it. Okay, transaction succeed. And if we check the balance again, let's see the balance. We can see the balance is 0. Okay, so this is how we can create the smart contract of the token, solely on the token. Okay, and then deploy it and interacting with it. Okay, locally, on the Ganesh forked blockchain. Okay, so you can also do it in a real blockchain with the same method, with the same process. Only okay, the one change is that you replace this URL with the node URL. You can find, you can register on the Alchemy. Okay, here as I show you just now, Alchemy. Yes, the quick node on Alchemy. Okay, yes, quick node. So this is the first smart contract I will introduce to you. And another smart contract is smart contract with some additional function to the token itself. So I call it the storage token, which means that, let me check it. Okay. So see the smart contract, it has mainly two functions. The first is store. Okay, you store some number here in this variable. Oh no, in this variable. And then once you store a number, you are mint with some certain amount of the token. And once you retrieve the number, you will consume some token on hand, which means that some of your token on your address will be burned. Okay. Then we actually combine or integrate some functions of the storage smart contract with the token contract. Okay. And you can see here, I made a smart contract, this smart contract, and name it as a storage token, also heritage from the ERC20 smart contract, and also vulnerable. Okay. Ownable means okay, some of the certain functions can only be changed by the owner. Here is the reward rate, okay, fee rate, which means the amount of token given to the address when some certain address is updating or uploading some data, as well as the fee uh, deducted from certain address of the token. Okay. And other things mean are the same. Okay. And you can check the details by yourself when I upload the code. And I also write a API for interacting with this smart contract. Okay, so here the API in the same logic. Okay. Um, okay, not deploy. Okay, this is unnecessary. The first is store. Okay, you store a number. Okay, the only import is the number. Once you store the number, you get some token as a reward, and also you can retrieve the data. And when you are retrieving the data, you are actually consuming some of your token on hand. Okay, and you can also view the data. Okay, and you can also check the balance of your token on your hand, because the smart contract is a heritage from the ERC20 standard. So the balance of function would, and as well as the transfer function, would be also heritage from the ERC20 standard. And remember the question proposed by one of you just now, how the mint will be included in a smart contract. So just now, only the admin can give some certain address, a certain amount of the token. But now here we wrap this mint, okay, inside the we store the mint function inside the store function. So okay, so only one user okay update the storage variable, he can get some rewarded token. Okay. And the deployer here we use the CM, so I will not discuss it again. And here's the test script. Okay, so basically, the code for deploying the smart contract would be same, so I will not discuss that again. The only difference is the API we use to interact with this smart contract. So let me firstly deploy it. Okay, so I get some questions. So, mm, for what purpose we pass then fork and deterministic when uh so these you mean the Ganache, okay. So the Ganache network is the local fork of the real network, which means that we can simulate the transactions or simulate our smart contract locally on the Ganesh fork. Okay. Usually we do this for testing our smart contract. Okay, think about the case you are designing and launching a website. Okay, so before you are really launching the website on the server and open it to the public, you need to simulate on your own computer locally. Okay, so this kind of behavior is very similar to the case what we are doing on the Ganesh local fork. Okay. And the second one, do I correctly understand that we even cannot to define mint and burn functions since they are heritage from ERC20? Yes. So if you are making your smart contract based on the ERC20 standard, you cannot modify it. So, but you can write your own ERC20 standard. So in that case, you can change it. But for the heritage, you cannot change it. You can only add some additional function to it, but the function inside, you cannot change it. So I think it's the same with the Python programming language. Even I cannot recall it clear, but the heritage function can be classified into several groups, right? For some of them, you can change it. For some of the others, you cannot change it. And the mint is the group that you cannot change it. So the exact definition of the function you inherited, you need to check from the standard. Okay, and in the standard, it will tells you which group you can change it in the some classes. Okay, and which kind of function you cannot change in the some classes, which means you can be overwrite by the functions in the some functions. Okay. And do I correctly understand that we cannot infinitely mint and burn tokens for our account locally since we will spend gas each time and for the gas problem, because we are simulating it locally, and in the simulating case, you will have a fake account, and on the fake account you have a 100 ETH. And that 100 is can support a lot of transactions. So theoretically, there will be a limit of the maximum number of transactions you can make on the local network. But actually, in reality, it's unlimited because once you uh, exhaust it, you can just shift to another account, or you can just restart the local fork or do something else. You can read the instruction of the Ganesh. Okay, so because it's just a simulating, so you are not encounter the case that your gas on the account is not enough to support you to do the simulation. Okay, this can be avoided. Yeah. And here, yeah, this is a very common problem we usually encounter. So it says that the transaction cannot be replaced. Mining has already started. So remember the case of the nonce. So which means the every account can send the transactions once at a time. So if we are doing the transaction in two console, here I do it actually in two console with one address, there may be some conviction. So in this case, we just restart the local fork. Most of the problem will be resolved. So let's restart it. And yeah, so okay, we restart it and we shift to the test. Okay, the test things. Test the storage token. Oh, test the storage token. And then run it. Firstly, we deploy it. You can see that this smart contract has been deployed on this address. Okay, and then we do the same. Okay, we create the local Python instance of the smart contract because we are now have deployed the address of the smart contract. Okay, we run it, and then let's test this function. Okay, let me unmute it. Okay, firstly, we check the balance of the account. Okay, so account is the account we use to deploy it. Okay, here we want to check the balance of the account generated by this private key. And we use this private key to to init the storage token API. Okay, here the storage key. So the balance of it should be 0 because we didn't do anything yet. Okay. Oh, there is some initial balance. Okay. So it may be because I did some test before I open this. I start the course, and because I'm using the deterministic mode of the Ganesh, so it will remember something. But let's further test the store function. Okay, the store function means that I uh, give the value of 42 to the variable we defined at the beginning of the storage contract. And then, okay, and then after deploying it, after it, I will have 10 additional token. So let's check it. Firstly, give the number to the variable. Okay, success. And then let's check the balance again. It should be another additional 10 tokens. Okay, so we can see that there is 10 additional tokens. And let's view it. Okay, in my definition, okay, in the smart contract, in my definition of the smart contract, the last variable input in the constructor is the fee that will be consumed by each call of the view, the retrieve function. Then, which means that in the constructing, we define the fee level. Okay, the fee level is defined as 1, which means that every time you retrieve the data, it will consume you 1 token. And because now we have this much of the token on the balance, so after one calling of the of the data, we will have 1 token deducted. Okay, so let's try. and the transaction succeed. And then we check the balance. We can see that there is actually one token deducted. Okay. Yeah. And then we store the number we stored at the beginning. It should be 42, right? And we will check the store. Okay, the store number is 42. Okay. So as time limit, I only generally talk about how the things are working, but you can check the detail by yourself on the repo. I will push all the code to the GitHub later on. But yeah, we're almost at the time. So do you have any further questions? Yeah, I gonna share the link to the GitHub later after I push it. Yeah, no, I haven't pushed it yet. Yeah, yeah. Yes. So I think it's time. So later, I think as usual, half an hour later, you're gonna go to another course of the AI. So let's have a half hour break. Yeah. So thanks for your attending.